right. So 8.4 is a side-splitting theorem. Side-splitting theorem is just another tool that we can use to talk about similar triangles. So I'm going to write the theorem, and then we'll draw a picture and talk about what it means. So the side-splitting theorem says that a line parallel to one side of a triangle divides the other two sides proportionally. And remember, proportionally means same ratio. So let's draw a picture of what we're talking about here. So here's my triangle. And here's the line that's parallel. And remember that the arrows mean parallel. Arrows mean parallel. So I'm going to label these the parts of this triangle.
That's what I just said. Or during the summer.
All right, so here's our triangle. Here's the line that's parallel to the one side of the triangle. Remember that arrows mean that the lines are parallel. And I just labeled the various parts of the triangle. This A is the length of this segment, B is the length of this segment, C here, D here, E and F. The side-splitting theorem gives us a bunch of proportions that we can work with. So I'm just going to list a few of them. For the side-splitting theorem, I can say that A over B equals C over D. This part here divided by this part equals this part divided by this part. I can say that A over F equals C over E. This upper part here divided by the whole length of this side equals the upper part here divided by the whole length of that side. I can say that A over C, the two upper parts, equals B over D, the two lower parts. And let's do one more. Let's do B over F. Chapter 8 is pretty straightforward because it's all these proportions. B over F equals D over E. So these are four of the proportions that I can set up using the side splitter theorem. All of these proportions come from this line being parallel to the base of the triangle. I can set up all these proportions. So whenever we have a situation where we have a line parallel to one side, we have all kinds of proportions that we can work with. And side-splitting theorem, similar triangles, it's a really powerful tool. In my calculus class, we use similar triangles frequently to solve problems. So it's not something that we just learn once and forget about. Even if you go on in math, you use similar triangles for lots of things. You use them for solving problems in science, in lots of different areas. So it gives you a really powerful tool. Questions about the side-splitting theorem? So let's look at some examples of using the side-splitting theorem. So here's our triangle for our first example. Let me make that black here. So here's my triangle.
I'm gonna go.
Almost opposite by that. That was funny.
So this is 9, this is 3, this is 6, this is x, and we're going to say that this side is parallel to that side. Remember that the arrows mean parallel. So, and we want to find x.
2.
So I can set up a bunch of different proportions. The first one that I think of is, I'm going to say 9 divided by 6. I'm going to do the top part divided by the top part equals the bottom part divided by the bottom part.
So A and B equals C and B.
Right. And then I cross multiply. 9x equals 18 divided by 9, and x equals 2.
Mr. Bean,
Mhm.
couldn't you assume that since it's 3 and 9 and 2 and 6, since 3 doesn't amount to a time, you should remember 6 3 times? Or is it just not?
I still know how to do this.
Which part?
All of it. It's not that much.
Um,
Or something. I don't get it.
If the numbers weren't as straightforward, we would have to set up and cross multiply. These are easy numbers, so it works out nice this way. I could also, listen up guys, I could also set it up. I could say 9 divided by 3 equals 6 divided by x. I could set it up that way, and I still get 9x equals 18. I get the same thing that way. So I can set it up several different ways. Well, we set up a proportion with the part that we're looking for. All right, let's look at another example. This one's a little different. So here's my triangle for this one. And we're going to say that these two sides are parallel. Remember, the arrows mean parallel. This is 3, this is 4, this is 2, and this whole side is x, and we want to find x. We only know part of it. We know this part. So we want to write a proportion with x as one part. So x is this whole side of the triangle. So if we wanted to write a proportion with the whole side of the other side of the triangle, how long would the other side be? This part's 3 and this part's 4. So that whole side would be 7. So we can write a proportion with this whole side to this whole side. So I'm going to say 7 divided by x equals, and then I have these two parts, 3 divided by 2. So I get 3x equals 14 divided by 3, and x equals 4.66 repeating.
Why did you decide to do the 3 over 2?
Because I have this part and I have this part. So otherwise I would have to do 4 and some, yeah, I don't know that part, so I don't have anything else to go with that one. Yes.
So when you're doing it, you have to make sure like the top line are both on the same side and the bottom are both on the same side. So like the 7 and the 3 are both from like the same side. of the
Right,
triangle.
right. We could now now on this one we could say 9 divided by 6, that 9 divided by 6 equals 3 divided by x, or I could say 9 divided by 3 is 6 divided by x, as long as we keep the parts that we're using in the same place in both fractions.
Okay.
Does that make sense?
Yeah.
Okay. Now let me do one more example with side splitting where we have to be even a little more careful. So here's my triangle for this one. and these two are parallel. Remember, the arrows mean parallel. And this is 4, and this is 6, and this is 2, and this side is x, and we want to find x. Now if we write our proportion, if we write one ratio with x, I could say that 2 divided by x equals, and we need to write a different, another ratio. Now what part of the triangle is, of this small triangle, let me highlight the small triangle. What part of the small triangle is 2? The base, 2 is the base, and we're comparing it with the base of the bigger triangle. X is the base of the bigger triangle. 4 is the side of the smaller triangle. What's the side of the big triangle? 10. We have to add these together. 6 is only this small part. So for this kind of problem, you have to be very careful. If you're comparing the two triangles, make sure you're comparing the parts of the two triangles. 6 is only this small section here. So we have to compare the side of the small triangle, which is 4, with the whole side of the big triangle, which is 10. So with this kind of problem, you have to be sure you're being very careful with the parts that you're comparing. And then we'd say 4x equals 20 when we cross multiply, divided by 4, and x equals 5. So make sure you're comparing the same parts. Questions on that example? This particular type of problem tricks people often. So make sure you're keeping straight what parts you're setting up your proportions with. All right, let's talk about a corollary of the side-splitting theorem. And a corollary, just as a reminder, means a theorem that we can figure out easily once we know our first theorem. So our corollary says that 3 or more parallel lines divide two intersecting transversals proportionally. So let's draw our picture to see what this is telling us about. And I'm going to make my transversals red. So there are my intersecting transversals. And here are my 3 parallel lines. So I'll make my arrows here, so that way we know for sure they're parallel. L is parallel to M, parallel to N. And we'll call this line S and T. S and T are transversals. So these 3 lines, these 3 parallel lines intersect these 2 red transversals that intersect here. Let me label some points and we'll write some proportions. This is A, this is B, this is C, and we'll call this x, y, and z. So what the side-splitting corollary tells us is if we have these parallel lines and these transversals, that we can say that AB divided by BC, so this length divided by this length, equals XY divided by YZ. So that's one proportion that we can write from this. We could say that AB divided by XY, this length divided by this length, equals BC divided by YZ. This length divided by this length. So it's very similar to what we did with the triangle. Let's just do one more. There are a bunch more that we could write. I could say that AC, this whole length, divided by AB, equals XZ, this whole length, divided by XY. So those are three of the proportions that come out of this, out of the side-splitting corollary. There are a lot more that we could write. These are just a few of them. Same idea as we used with the triangle. We just need to make sure we have the parts that we're using in our proportions in the same part, in the same place on both sides of the equal sign. Questions on this? All right, let's look at an example using side splitting, or using the corollary. So our example, here's our picture, and I'm going to get rid of my arrows here. And all four of these are parallel. This is 40 yards. This is 50 yards. And this is 62.5 yards. This is X. This is Y. And that's 80 yards. So this line here and this line are my transversal. Eventually they're going to intersect because they're not parallel. Eventually they're going to intersect. So these are my intersecting transversals. We have these four parallel lines that cut these intersecting transversals. So our sides are proportional. To find X and Y, I just need to make a proportion with the part that I'm looking for. So I'm just going to pick the easy one here. I'm going to say that 40 divided by X, this part divided by this part, equals 62.5 divided by 80. I just have that one and that one. So those are parts that I know, and I need to figure out X. This tells me that 3,200, when I cross multiply 80 times 40, equals 62.5 times X, divided by 62.5, and X finally equals 51.2. So we figured out that's 51.2. And I do the same thing to find Y. I'll just use the same segments that we used before. 50 divided by Y also equals 62.5 divided by 80. I could have used 50 divided by Y equals 40 divided by 51.2. That would give me the same answer. So I get 62.5 Y equals 4,000 divided by 62.5, and Y equals 64. So using the side splitting corollary, I set up my proportions, and I can figure out x and y. And if we had more that we had to figure out, we could figure out as many of them as we wanted because they'd have to have the same ratio. Questions on that? All right.